So we can plot the progress of a chemical reaction in terms of energy versus reaction pathway. And these kinds of plots are called reaction progress diagrams or reaction coordinates. So I want to teach you how to draw and analyze a reaction progress diagram in this lecture. Let's take an example reaction where we have carbon monoxide reacting with nitrogen dioxide to make carbon dioxide and nitrogen monoxide. And I'm telling you that this is an exothermic reaction, so heat is going to be released over the course of this reaction. So in the previous lecture, we talked about activated complexes, this high energy state in a reaction where we have bonds partially broken and bonds partially formed en route from reactants to products. So let's draw out some of the bonds in the reactants here. Carbon monoxide has a triple bond. I'm not drawing the whole Lewis structure. I'm just drawing the bonds, so we can kind of imagine the bonds in the reactants being broken, and then new bonds forming to make products. So carbon dioxide, there is a linear molecule, and nitrogen monoxide would be kind of analogous to carbon dioxide, just looking at the bonds. So we need to think about how bonds are broken in the reactants and bonds are formed to make the products. We can plot the progress using a reaction progress diagram. So when you draw a reaction progress diagram, you have energy on the y-axis, and then on the x-axis, it's not exactly time. It's something that we call the reaction coordinate. Sometimes you'll see it written as the reaction progress. And what it does is it shows how the energy varies in the reactants and products as a function of time. So for this particular reaction, we were told that it's an exothermic reaction, so energy is going to be released over the course of the reaction. So that means that if we look at the energy of the reactants, I'm just going to arbitrarily put it here. Okay, so this is, I'm going to label it in red. This is the energy of the reactants. The reactants being the CO and the NO2. That energy of the reactants is going to be higher energy than the energy of the products. I'm going to just stick a line down here. The reason is I know it's exothermic. So I am going to start out at a higher energy and end at a lower energy because the difference is going to be released in the form of heat. So this final energy would be the energy of the products. In this case, the products are the carbon dioxide and the nitrogen monoxide. Okay, so what happens in between? What we just did basically is a thermodynamic thing. We take the final state minus the initial state, we get the delta H for the reaction, right? But there's a pathway that occurs in between. Now, in the reactants, bonds start to break and new bonds start to form, and that creates a very destabilized species. So the energy is going to go up. The energy is going to peak where we have the transition state or the activated complex. And then it'll come back down and we'll ride down the hill all the way to the products. So we'll get a curve that looks something like this. And that's a little bit ugly. So let me try to do that again and make it look a little bit nicer. It's a bit hard with the stylus. So it looks kind of like this. Okay, and again, I don't need to have this weird little wonky thing here. So let's just try to do it all in one blow so we have a smooth line. All right, that's a little bit better. So there are a few things here that we need to notice. I'm going to make just a dotted line here. The difference between the starting energy and the final energy here, that's going to be the delta H of my reaction. Okay, so that's the amount of heat that's going to be released as the reaction goes from start to finish. Okay, the delta H of the reaction is literally the final energy minus the initial energy. The difference between the energy of the reactants and this peak here, that is going to be the activation energy, EA. So the difference between the energy of the reactants and this maximum is referred to as the activation energy. Now, what is this maximum? This maximum is the energy of the so-called transition state. I'm going to abbreviate transition state as TS with this double cross. The transition state is also known as an activated complex, and it represents the species with the bonds of the reactants partially broken and the bonds of the products partially formed. So here we're going from carbon monoxide to carbon dioxide. So you can imagine that we're partially breaking the triple bonds on the carbon dioxide and partially forming a new bond between carbon and oxygen. Simultaneously, the bonds between the oxygen and nitrogen dioxide is breaking. And a new bond is forming to make a triple bond between nitrogen and oxygen. Now, that's a cartoon, right? It's not a real molecule, but it's meant to represent a transition state. So I'm going to give it this double cross superscript. That transition state is the maximum energy species in the progress of this reaction. So the difference between the energy of the transition state and the energy of the reactants, that's known as the activation energy. So literally, the activation energy is this barrier that you have to overcome in order to get from reactants to products. Okay, it's this mountain that we have to climb in the journey from reactants to products. Okay, so you really see how activation energy, E sub A, activation energy, this is a threshold energy. It's a barrier. Okay, it's a barrier that must be overcome, to produce a reaction, to go from reactants to products. So, to produce a reaction. Okay, so in this case, we saw how the energy of the products was lower than the energy of the reactants. And the reason we drew it that way is because we were told that it was an exothermic reaction, right? So we had a situation where the energy of the products, okay, so I can say when the energy of the products is less than the energy of the reactants, you have a negative delta H, or an exothermic reaction, at least in terms of enthalpy changes. So overall, there would be a negative delta H, negative delta H. So what would it look like if we had an endothermic reaction? Let's draw a reaction progress diagram for an endothermic reaction. Okay, so for an endothermic reaction, the delta H is going to be positive. And that means that the energy of the products is going to be greater than the energy of the reactants. So if I start down here for the energy of the reactants, that means the energy of my products is going to be higher. So what the reaction progress diagram might look like is something like this, where we still have an activation energy barrier, okay? And that activation energy barrier is still going to be the difference between the energy of the reactants and the energy of the transition state. Okay, so this would be the activation energy barrier. And once again, I should label my axes here. Energy is on the y-axis, and the reaction progress, or the reaction coordinate, whatever you want to call it, is on the x-axis. And here we have reactants. the energy of the reactants, and here we have the products. And up at the top, I'm just going to label this, we have the transition state. Okay, so once again, the activation energy barrier is the difference between the energy of the transition state and the energy of the reactants. And it's the barrier, the threshold that has to be overcome to go from reactants to products. In this case, we have the difference between the energy of the products and the energy of the reactants, once again, giving us the delta H of our reaction. And we can see how, because the final state exceeds the initial state, the delta H is going to be positive. And that's always going to be the case for an endothermic reaction. Okay, so what does this activation energy mean? Well, in terms of kinetics, it means that only molecules that have sufficient energy to overcome the activation energy barriers are going to be able to form products. Okay, so if the molecules don't have enough energy, they're not going to react. Okay, that's the consequence for chemical kinetics. So I'm going to make a different plot now, not a reaction progress plot, but the distribution of molecules as a function of energy. Okay, so the axes are going to be labeled differently here. Here are the number of molecules involved in my reaction, and I am looking at them as a function of the energy that they have. So this is an energy distribution diagram. Now, probably looks something like a bell curve. So I'm going to just draw something that looks like this. Now, let's say that my activation energy falls here. Okay, this is the value of my activation energy. So I'm going to go up and have this intersect my distribution curve here. What this means, let me kind of shade this in here. Okay, so this is the total number of molecules here on the y-axis, remember. So this means that only the molecules that exceed the activation energy, only molecules with greater than or equal to the activation energy are going to be able to become products. Okay, will be products, I mean, will form products really is what I mean. So only molecules that are kind of exceeding that energy are going to be able to form products. And what that means is that most of the molecules involved in the reaction typically are not going to be able to exceed that activation energy barrier. And in the next lecture, we'll talk about how you can get more molecules to exceed that activation energy barrier and therefore speed up your chemical reaction.